Hello everyone, welcome to lecture 2. So this is a lecture on fluid kinematics where we'll study the properties, the dynamics of fluid without considering the forces or the stresses that produce these motions. So flows can be are not varying with time, so these are called steady flows. So steady flows are flows that don't vary with time. This is just some definition that most of you might already be familiar with. Uniform flows, I mean, this is just to set the stage for the deeper discussion that we'll be doing. Uniform flows are flows that don't vary with time, that don't vary with space. So these are just some simple definitions. So we'll understand the fluid flow without really caring about the forces that are producing them at this point. Then we'll certainly, of course, go to flow dynamics. So there are two ways to describe the flow field. One is the Lagrangian and the other is the Eulerian description of fluid flow. So Lagrangian description, in this description, so fluid elements are followed the whole system, or um, the volume of interest. So by fluid element, I mean a certain portion of the fluid that is of interest to you. For example, if there is a pipe flow and you choose a certain uh, portion of your interest and you follow this this element as it goes along in this pipe. So this is the system or the volume of interest that I'm talking about. So here pipe is the volume or the system of interest. So in this, every particle is labeled by R naught at time t naught. So for example, this let's draw a coordinate system which is in x, y, and z. So we'll always be working in three-dimensional Cartesian coordinate system in this course, and we have a fluid element which was initially at R naught at time t naught. So this is the origin, and the fluid element which I have represented it here, let's say this is the part, this is the element 1. This was at position R naught in time t naught. T naught is a reference time, you can take it to be 0 without any loss of generality. So this element was at position 1, and this has moved, this is the particle path, and this has moved to a certain position, let's say this position R. So this is the position 2 where it has moved to, and this location is given by R. Now R is a function of time, of course, but this one is also a function of R naught and T naught, because we need to identify that this is the position of the particle which was initially at position 1, okay, which is given by R naught at time T naught. So this specifies the flow field. So please here it is to be noted that R naught depends, sorry, R depends on R naught and T. So here in this course, this arrow notation means it's a vector. So R is a vector. Anything on any arrow on top of a quantity is a vector, and R naught is of course the initial vector. So this has an arrow on top. So in this Lagrangian description of flow field, velocity v can be represented as the rate of change of the position vector r, and this is dependent on the velocity. This is the velocity of the particle which had started at r0, and now the velocity at time t. Similarly, acceleration is just the double derivative of the position vector of the particles which had started at r0. Okay, so this is the double derivative of the position vector or the first derivative of the velocity vector. So this is the Lagrangian description of the fluid flow. Now the Eulerian description of fluid flow. So these are all basic fluid kinematics. Eulerian description. This is needed because we are developing the equations of motion, but we need to first recap to understand the derivations that we are going to do very soon. So in Eulerian description of motion, a fixed region of space also called the control volume is examined to study the flow dynamics. So this is a convenient way. This is a more convenient way than following the fluid elements. Fluid elements, fluid by its nature is deformable, and hence it is actually cumbersome to keep following a certain fluid of interest and then measuring its properties as the fluid moves through that volume of interest. Let's say it's a pipe or a channel. Whereas in this Eulerian description, we fix a region of space that's called also the control volume. For example, let's say you want to understand flow in a cylinder, in a pipe. We have a set of region which is our test section. We put a camera on in that test section, or let's say we put a temperature probe at a certain point and we measure the temperature. So these are different techniques. I mean, these are all Eulerian techniques to understand the flow dynamics. So this is more convenient because it's very difficult to keep following the fluid elements. Whereas if you recall, I mentioned that there are moving platforms, for example gliders, which can measure quantities of interest in geophysical flows, for example in an ocean, by moving along with the currents. So there are Lagrangian floats which move along with the currents at a certain density level. Weather balloons are something which also move as the air goes up. It exactly does not follow a certain movement of an air parcel, but of course it's a moving platform. These can be done, but these are, as you can imagine, are cumbersome. So that is why we need an Eulerian approach. So this is a field-based approach. So this is a field-based approach and involves three spatial coordinates, x, vector, and time. In 3D, as I mentioned, all of our studies are in 3D Cartesian coordinate system. So this is a involves all the three directions, three orthogonal directions, and time. So any vector or scalar quantity for example, let's say B can be represented as B, which is a function of the spatial coordinates and time. So this is there's a field variable, that is it depends, it has a spatial and a temporal dependence. So in this method. So even though this makes things easier for us in terms of measurements, however, the calculation of acceleration in this frame of reference, in this measurement technique, that is the Eulerian measurement technique, is not very straightforward, whereas it was straightforward in the Lagrangian description, Lagrangian methodology, because the motion of the fluid element was exactly followed, whereas this is not the case in the Eulerian description. Now, as we try to measure an acceleration, you will realize that the fluid particle has already changed its position, and hence we need a better, or we need some kind of a mathematical rule to get to the acceleration of that fluid element because of its change in position as well as its own temporal evolution in time. So this is what we are going to do now. We're trying to find out a form of the acceleration of any quantity in the Eulerian frame of reference. So next we derive a form of the acceleration. So let's say so this quantity b should be equal. So regardless of the Eulerian or the Lagrangian description, this quantity b should be equal if the position at which you are measuring the quantity is same when okay. So if x, this spatial coordinate, is same as this spatial coordinate r, then in this case the whereas regardless of whether you are doing a Lagrangian measurement or an Eulerian measurement, both of these variables should be same. I mean, the system does not care how you are measuring. It just cares. I mean, it's just doing its thing based on the laws of physics. But because you have changed your measurement technique does not mean the physics of the problem changes. Hence, at that location, given that you use the same coordinate system and you use the same clock to measure time in both the measurements, if this is the case, then this should hold. This should always hold. The quantity in the Eulerian technique should be equal to the quantity that is measured by the Lagrangian technique. So now, applying derivative to the left hand side, so d dt of this quantity b, which is a function of the position vector r, which in turn is a function of the initial position vector. So there are all arrows, sometimes I might miss, but all of these are vector quantities. So we'll do the expansion of the derivation in the next slide. Okay, so this is how the expansion looks like. So there'll be del r1 dr1 by dt. So r1, r2 and r3 are the components of the r vector, and when I say del, I'm referring to the partial derivatives here, and I'm used to calling the ordinate derivatives as d dt. So this is dr3 by dt plus del b del t. Okay, so this is the expansion. Now when x is equal to r, t r naught t naught, the left hand side is equal to the right hand side. So both the Eulerian and Lagrangian descriptions match. So now the right hand side, from the earlier slide, is the measurement in the Eulerian description. Right hand side is the variable in the Eulerian description. measured in the Euler linear description. And so just equating both of these, del B del R1 del R2 dr2 dt plus del B del R3 dr3 dt plus del B del T is equal to d dt b x comma t when x equal to r. When x equal to r, this left hand side and the right hand side should be equal. As the partial derivative of the position vector is the velocity vector, that is, I'm writing in component form, the partial derivative in one direction is the velocity in that direction, and the partial derivatives of b with respect to any one component of r can be represented as del b del xi when x equal to r. This is what we have been saying. This is the third time we have said this, x equal to r. So we can write this. So we expand the previous expansion as so. So d dt of b, which is a function of r and is a function of r naught and t naught, is equal to del b del x1 u1 plus del b del x2 u2 plus del b del x3 u3 plus del b del t. So now these can be clubbed and written as the u vector dot this new symbol that I have introduced. Probably some of you are familiar. This is the del operator. This is a vector operator, and this quantity b plus the rate of change of b with respect to time, and this one is given a form which is given by capital D dt. So this is the this total rate of change of this quantity with time. So this is what I mean, this is what we are trying to find out. I mean, how does the rate of change of a certain quantity um, can be represented in the Eulerian frame of reference. So this is what we have arrived at. So this is called the total time derivative in the Eulerian description. This is also called the material derivative. So this is called the material derivative or the substantial derivative. So this is the total time derivative in the Eulerian description. In the Eulerian description of motion. And this term is known as the advective rate of change. So this is called the advective rate of change of B, and this is the local rate or the temporal changes of B. So local rate of change or temporal change of P. So these two terms give us the total derivative, which is called the material derivative or the substantial derivative, and this is represented by this symbol of capital D dt. So this is the total derivative in the Eulerian frame of reference. So d dt has meaning only when applied to a field variable, that is only when B is a function of the spatial coordinates and time. So this has to be a field variable, otherwise it does not make sense. So there are again some basic definitions which some of us may have already gone through in the basic or intermediate level fluid mechanics. So this is just to set the stage for something that is that we are trying to relate the Eulerian and the Lagrangian description of motion, because we want to make sure the conservation laws are valid when we are using an Eulerian description of motion also. So but just before getting there, just we'll have some small definitions. So first of all, for a system, a system briefly is just a set of particles which is of our interest. This is, you can word it in any way that you like, and again I'll give the example from pipe. So if you are interested in this in these set of particles, this is your system. The system can be the whole house that you are sitting in right now, or the system is a car, or system is the engine of the car. So system is anything that you are interested in. But in our course, for our study, system is just the set of particles or fluid particles, fluid elements that you are interested in for your for doing the whatever the analysis that you are going to do after this. So if we are tracking a system, we are actually applying a Lagrangian approach. As you might recall, I had drawn the same diagram when I was describing the Lagrangian description of motion. So when we are tracking a system, we are essentially employing a Lagrangian description, a Lagrangian technique. And the other definition, control volume, which I had mentioned previously during the Eulerian description of motion, is that I mean, this was of control volume. And just to briefly describe what this is a region in space which is bounded by a control surface. There can be various different wordings, but this is just a region in space which is of your interest and is bounded by a control surface. So again, giving the explaining it through a pipe flow, if this is your region of interest, this is where you want to do some measurement. For example, you have a temperature probe here, or you have a camera which is looking into this, and then you are measuring some velocity field. This is your region of interest. So this is your control volume, and this is bounded by a control surface. So the control volume can be moving, it can be fixed, or it can be moving. Okay, so it does not have to be always stationary. For example, the whole aeroplane can be your control volume, as you are looking, if you want to look at some dynamics of the flows around the aeroplane. So that can be a moving system. The whole car can be a control volume if it is of your interest, if it's something that you want to understand. So but we are not essentially following a certain set of particles. So which means we are essentially employing an Eulerian approach here. So we have fixed a region in space that we'll always study. For example, this, as I've given you, this is a channel flow, this is a pipe flow, this is a region of study, and we have fixed it. This whole thing can be moving. It can be on a trolley, it's moving, but you have fixed your region of interest and you are measuring doing some measurements in this region, and this is called the control volume. So going from systems approach to control volume approach. So the reason why this is essential for us is that the systems approach, which is essentially Lagrangian description, is cumbersome, as I mentioned previously. It is difficult to follow a set of particles, set of fluid particles, because of its deformable nature, and do all the measurements. So we employ a control volume technique. So we fix our region of interest. So we need to go from systems approach to control volume approach. But Newtonian laws, the conservation laws, were developed for systems. So these hold exactly for systems. So for example, the first law of thermodynamics, Newton's second law. So however, I mean, because it is very difficult for us to keep track systems of deformable systems like fluids, I mean water or gases, liquids or gases. So I mean, we employ a control volume approach. So we fix, so to apply the conservation laws, we need to go from a systems approach to control volume approach, and we need a mathematical transformation. We need a transformation rule. So we need a rule or a mathematical transformation. To go from the systems approach to control volume approach. Okay, so that we can modify, we can apply the conservation laws, we can apply the Newton's laws in the control volume approach. So we need a way to, we need to develop a mathematical transformation in how we should change the equations, what new terms we can introduce, so that the conservation laws are also valid in the control volume approach. So this mathematical transformation or this rule is obtained, this connection between the systems approach to control volume approach is obtained by a certain theorem. This is called the Reynolds transport theorem. So Reynolds transport theorem, the derivation of this, we'll be doing it in the next lecture. So this is Reynolds transport theorem, gives us a mathematical transformation, and as you can imagine, so this is important for us to understand both the systems approach and the control volume approach, because in the introductory video in the lecture 1, I showed that our measurements in the ocean and the atmosphere can be both in a fixed platform or a moving platform. So if you want to apply the conservation laws to a fixed platform, then we need to have an appropriate way of representing the form of the conservation laws, so that the conservation laws are also valid, which were initially derived for systems, and they hold exactly for systems. So that is the reason why we need to go deep into the Reynolds transport theorem. And as you will also see that the Reynolds transport theorem will also help us to derive the equations of motion and the conservation laws. And in the lecture will show that how this what is the mathematical form of the Reynolds transport theorem, and how both the equations of the conservation of mass and conservation of momentum can be derived from this mathematical transformation. So thank you.